In calculus, particularly in integration, there are times when you can only do the integration after doing partial fractions. In other words, you will be given a function that is in the form of a fraction, and before you integrate that function, you would have to you should split it into several fractions. Then it becomes easier to integrate that function. But then what do you rely on? You are going to rely on formula, and you are usually given these formulas on your formula sheet. For example, the formula that we have here, and the formulas depend on the format of the denominator of that fraction. Like in the first case here, the denominator is a linear function that is raised to a power n, and this is the general form of the partial fraction. Like if you split those functions, if you split the fraction, you're going to have several fractions with denominators raised to the power 1 until the highest power there. So if, let's say, this power here is 4, it means we are going to have fractions with the denominators ax plus b to the power 2, ax plus b to the power 3, until ax plus b to the power 4. This is the general form of those partial fractions that you're going to form. And here we have one linear factor raised to a power as our denominator. Then this is the format that you get here. Then in the second case, we have two linear factors as denominators raised to different powers, or raised to different powers, whatever it is. In this case, we have to power 3 to power 3. It can be to any power, by the way. This is the general format. Then the last format, which is very, very important because it is quite different from the rest. What we have here is a denominator which has two factors. One of the factors is a quadratic function that cannot be factorized. Please take this carefully. One of the denominators is a quadratic function that we cannot factorize. If we have that, this is the general form of the partial fractions. Look at this part here, where we have this quadratic function as our denominator. The numerator, we assume that the numerator is going to be a linear function. That is the assumption that we make. So when you are doing partial fractions, what you're essentially doing is finding these constants, the a, the b, the c, the z, etc. That's what you're finding. All these, you have them. Obviously, you'll be given the ax plus b. It will be a linear function like 2x plus 3 or whatever you have there. But all you have to find are the constants, these constants in the numerators. That's what you have to find. So all you're doing is knowing the solution that you have, choosing the correct formula, and then solving for A, B, C, and D. This is what I'll be doing in this in this video. I'll be explaining how you solve for A, B, C, and D. Yes, in different syllabi, you may find different formats of the partial fractions. It really doesn't matter. The approach is the same. You just need to know these general forms, which you'll be given, by the way. In most cases, you're given on your formula sheet. You just have to go to the formula sheet, check the situation that you have, and apply the correct formula. Enough of this. Let us go to the question that we have here. So I'm going to do one example. I'm going to do one example in this video, but I will explain thoroughly for you to get what happens in other cases that you may encounter. So let us go out here and come here. Now, what we have here is we are required to find this integral. This is integration. We are required to find the integral. However, if we look at all the techniques that we have learned about integration, we find that we can only or we can do this easily if we do the partial fractions first. In other words, we have to go to this fraction here and split it into 2 or more fractions. Then we can integrate separately those fractions. That's what we can do. But before I start the process, I want to mention something. We can only do these partial fractions for a proper fraction. We should have a proper fraction. It is quite easy if we're dealing with numerical fractions. It is quite easy for us to spot that, oh, this one is a proper fraction. If I have 2 over 5, this is proper. But if I have, let's say something like 10 over 7, this is improper because the numerator is bigger than the denominator. That's what we call improper fractions numerically. Now the question is, how do we see that we have an improper algebraic fraction? Because this is an algebraic fraction that we have here. How do we know that it is a proper fraction or it is improper? This is what you look at. If it is a proper fraction, degree of numerator, so let me write this, degree of numerator, the degree of the numerator will be less than the degree of the denominator. Degree of denominator. Degree of denominator. This is what you look at. It should be less than, always. If it is not less than, it is improper. If we look at our case, this is our numerator. X squared plus x minus 7. The degree of that, what we call the degree of a function or polynomial, it is the highest power of the variable. So in this case, the highest power of x is 2. So numerator here, the degree is degree 2. Then we go to the denominator. The denominator, it is degree 2 again. Then we have an improper fraction here. So this whole fraction that we have here is improper. It is improper because the degree of the numerator is the same as the degree of the denominator. It should be less than. If it is not less than, it is improper. So an improper fraction, it is an algebraic fraction in which the degree of the numerator is greater or equal to the degree of the denominator. That is an improper fraction. Now that we know that is an improper fraction, so what do we do? This is something that you should know here. We know it's an improper fraction. What do we do then? Because we can only do these partial fractions if we have a proper fraction. But because we don't have a proper fraction here, convert to a mixed fraction. Convert this to a mixed fraction. This is what you do first before you do your partial fractions. Now, I want to highlight this because it is important. Most of the time, people know how to do partial fractions, but if they are given an improper fraction, they may not do it right because they haven't followed this rule that you only do the partial fractions after converting to a mixed fraction. If we don't have a proper fraction, we cannot do the partial fraction. So what you do, let us say we have an improper fraction here, 10 over 7. If we divide 7 into 10, we get 1 remainder 3. So this 10 over 7 can be written as 1 plus 3 over 7. If you see what I did here, this is the remainder. This is our divisor. This 1 here is our quotient. We do the same with these algebraic fractions. We convert it into this format where you have a quotient plus remainder over divisor. Then this part here will always be a proper fraction, and that is what we do the mixed the partial fractions on. That is what we do. Now, I have done this with numerals. What about if we're dealing with what we have here, which is an algebraic fraction. This is what you do. So this is what you do if you're dealing with an algebraic fraction. All you do, you use a long division. You use long division, or so here use two methods. You can use long division. If you have forgotten how to do the long division of algebraic functions, or all you have to do is just to algebraic expressions, you just check one of the videos that I did. I'll put the video in the description below. Now you have to use long division. If you use long division of these algebraic expressions, you are going to have a polynomial plus an algebraic fraction. Then you can integrate those, or you can do now the partial fractions on the proper fraction that you get there. Or else, the other method that you can use, you just use some simple algebraic manipulation. Simple mathematical manipulation, in short. You just manipulate this and you see it just coming right. That's what I'm going to use here because I have seen something. So as long as you see something, you can use this as your starting point. Now I'm going to clear my board, then I start doing this question. Please follow clearly what I'm doing. I'm going to forget about integration for now and focus on the partial fractions. And in most cases, in most questions that you're given, most of the marks actually come from doing the partial fractions. The integration part will be quite straightforward. So let us do the partial fractions. I have here x squared plus x minus 7 divided by x squared plus x minus 6. I want to convert this to the format of quotient plus a remainder over divisor. In other words, into a mixed fraction. I don't want to do long division. What I want to do, I want to manipulate. So look at how I'm going to manipulate this. Let me use a different pen. I'm going to write this as x squared plus x minus a 6 minus a 1, all this over x squared plus a 6 plus x minus a 6. I'm doing this manipulation because I have seen something. I've seen that I can have the denominator in the numerator. So I'm going to split it like this. Now I'll have two fractions from here. I can have those two fractions from there. This is the algebraic manipulation that I was talking about. So we have x squared plus x minus 6 over x squared plus x minus 6. We can do this. I just want to highlight numerically. If I have 2 plus 3 over 7, this is equals to 2 over 7 plus 3 over 7. We are allowed to do this. It is proper mathematics. That's what I'm simply doing here, but with algebraic expressions. All right, let us carry on. Minus, or if I want to say plus, I can say that, but it's minus 1 over x squared plus x minus 6. Now, what I have here in the first part, this first part here, it is 1. It is 1. So I essentially have here 1 plus, no, not plus, minus. So it's 1 minus 1 all over x squared plus x minus 6. So what I have now, this part here, is a proper fraction. This is a proper fraction, and that's what I'm going to do my partial fractions on. I'm going to be dealing with this part here. I'll do the proper fractions on. But don't forget that you have this part, because both of them are important in your integration. We need both parts in our integration. I'm going to use this for to do my partial fractions. I don't want to do the long division. However, if you guys want me to do the long division, I can do it. Let me try to do the long division. It's quite fast. Please take note of this. Let me use another board. Okay, let me use this board. I'm going to do long division of the same function. So we have x squared plus x minus 6 dividing into x squared plus x minus 7. This is what we have, and everything is in order. We go to our divisor. This is our divisor. We look at it. It is written in decreasing powers of x. All the powers are there. Even if they are not there, it doesn't matter, but it should be written in decreasing powers of x. We come here to our dividend. It is also written in decreasing powers of x, and all the powers are represented. So we can do our long division. Now we say x squared into x squared, we get a 1. So we get a 1 here, a positive 1. Then we say x squared, no, we say 1 times x squared, we get x squared. 1 times x, we get a positive x. 1 times a minus 6, we get a minus 6. So after the multiplication, we do subtraction. X squared minus x squared is 0. X minus x is 0. Then minus 7 minus 6. This is like minus 7 plus 6. We get minus 1. Guys, this is our quotient. This is our quotient. This is our dividend. What we're dividing into, we call it the dividend. This is our remainder. We can no longer do the division anymore because x squared cannot go into minus 1. So we now have our remainder here. This is our remainder. And this is our divisor. And I said, after doing the long division, your expression now, which is f of x, you express it as 1 plus, no, let me use the general. You express it as quotient plus remainder over divisor. This is what you do. What you have here will always be a proper fraction. Always, it will be a proper fraction. What you have here may be a constant or a polynomial that you can integrate easily. This is what you have. So in our case, let us write our final answer that we should have from here. If we use long division, we'll still also have the same answer for x squared plus x minus 7 over x squared plus x minus 6. This will be equals to 1, our quotient, plus our remainder, which is minus 1. That's why we have a minus here. So minus 1 over the divisor. This is our divisor here. X squared plus x minus 1. I got the same thing using long division. So if you don't know how to do if you don't know how to do this, which is algebraic manipulation, it is not always possible, by the way. This happens if you can see that you can manipulate, go for it. It may be the easier way. If you cannot, obviously come here and do your long division, you will still get it right. Now we don't have to worry anymore about this whole thing, this part here. We are worried about this. This is what we want to do our partial fractions on. So I'm going to demonstrate how you do partial fractions using this, which is now a proper fraction. Let me clear my board and start fresh. So I now have 1 over x squared plus x minus 6. This is what I want to do my partial fractions on. We know that if we look at this and say, can we differentiate the denominator? Yes, we can differentiate the denominator. So the denominator is actually 1 over x plus 3 x minus 2. This is our denominator. It's x plus 3 and x minus 2. Please you check your factorization properly, because if you don't factorize well, you won't be able to do the partial fraction. So we essentially have 1 over x plus 3 times x minus 2. Now we go to our formula and we find that what we have here, the denominator is actually a product of two different linear factors. So the general form will be a over x plus 3 plus b over x minus 2. This is the general format. If you don't have the right general format, you cannot have the right answer. So from here, we are going now to look for a and b, which is what we do. I'm going to use one method, and in fact, yes, I'm going to use two methods. So both of the methods, I'm going to use them in this example, and you see what you do. So the first thing here is to get rid of our fractions. We get rid of our fractions, so we multiply throughout. We multiply by LCD, our lowest common denominator, which is this function here. So we multiply everything from here to there to there. We multiply by that denominator. If we do that, we're going to have 1, because here we multiply by this, we get rid of the denominator. A over x plus 3 multiplied by this, we get a x minus 2 plus b x plus 3. If we look here, I'm going to use the method of setting. I'm going to set x to be something. When I'm doing the setting, I know what I want to do. I want to get rid of, because this is, we have two unknowns here. In fact, 3 unknowns. We also don't know x. We have 3 unknowns and it's one equation. We cannot solve for 3 unknowns using one equation. So we have to eliminate 2 unknowns and have just one unknown, and we solve for it. So I'm going to set x equals to positive 2. I'm doing this because if I put x equal to positive 2 here, I will get rid of everything with a. I will be left with b. So if I do that, it means 1 will be equals to a times 2 minus 2 plus b 2 plus 3. Now from here, it is clear that this will become 0 and this is 5b. So b, in short, b is going to be 1 over 5. B is 1 over 5. So we have our b is 1 over 5. Good. Now let's go and look for a. We're going to use the same. So I'm going to put off this and put off that. All right. I'm going to use this part here. So I have I have 1 equals to a x minus 2 plus b x plus 3. Now I'm now looking for a. For me to look for a, I get rid of b. So I set x equals to minus 3. If I make x equals to minus 3, I'll get rid of this whole term here. Now I'll be able to look for a. From here we can say 1 is equals to a 3 minus 2 plus b, minus 3 minus 2, by the way, not 3 minus 2, plus b minus 3 plus 3. So from here we can say our a is minus 1 over 5. This is our a. So we have b as 1 over 5 and a as minus 1 over 5. We know this. So all right, let's come here. Let's put off this layer. So we got b as 1 over 5. We have a. So we have b as 1 over 5 and we have a as minus 1 over 5. I said this is one way of doing it. I was just setting and setting. Now, when it comes to this setting, you can set x to be anything that you want. You can set x to be anything that you want. You're allowed because it is an equation. As long as you use the same value of x throughout, it does not change anything. So you can set x to be anything that you want, but try to set x to be whatever gives you convenience. Now I want to use the other method. So let us close. Let's come back here and use the other method that I want to use. Let us clear this board here. I'm going to clear. All right. So I'm going to clear this part here. So let us clear this whole part here. Good. Now, so we have 1 over x plus 3 x minus 2, and we said this is equals to a over x plus 3 plus b over x minus 2. And if we multiply throughout, we got this function here that said 1 is equals to a x minus 2 plus b x plus 3. Okay, let us expand. This method involves expanding here. Let us expand this whole thing. If we expand here, ax minus 2a plus bx plus 3b. So I expanded here. So this was expand. This is the expansion. Then from expansion, group the like terms. Group the like terms. If we group the like terms, we have a equals to, I'm going to take everything with x, coefficient x together. So this will be a plus b. This should be equals to, no, a plus bx. So a plus b is the coefficient of x. Then we go to say plus everything. These minus 2a and minus 3b are constant. So plus minus 2a plus 3b. These are constants. I'm grouping them together. So it doesn't matter if you have x squared, x cubed, whatever it is, you can group the like terms together in this format. Then from here, you're going to compare coefficients. So what you're going to do here, you're going to compare. Actually, the good word is equate coefficients, the coefficients on LHS and RHS. So you're going to equate. If there's an equal sign here, it means the coefficient of x to the left should be equal to the coefficient of x to the right, and the constants to the left should be equal to the constants to the right. This should work. So we're going to start here. Let us start there. So we have 1 is equals to a plus 2b. Let's check. 1 is equals to a plus b. So 1 is equals to a plus b x plus minus 2a plus 3b. This is what we have. So compare. So let's start with coefficients. Coefficients of x. To the left hand side, the coefficient of x is 0. To the right hand side, the coefficient of x is a plus b. So a plus b should be equals to 0. Because on the left hand side, we don't have anything with an x. It means the coefficient of x that side is 0. Therefore, from here, therefore, a is equals to minus b. A is equals to minus b. We leave it like this. Then we go to compare constants. Compare constants. To the right hand side, this is our constant. It's minus 2a plus 3b. That should be equals to 1. Minus 2a plus 3b should be equals to 1 because the constant on the left-hand side is 1. But we know that a is equals to minus b. We know this. So where there is a, we can put minus b. So we have here minus 2 times minus b plus 3b is equals to 1. We are substituting using this equation 1. So this is sort of like our equation 2. From here, it means 3b. No, it means 2b plus 3b is equals to 1, which gives us 5b equals to 1. 5b equals to 1. Therefore, b is equals to 1 over 5. Remember, we got this answer already. We know this answer, but we're using a different method. This is the method of comparing coefficients, comparing constants, etc. And we take this back here. We know that a is equals to minus b, which means a is equals to minus 1 over 5 because b is 1 over 5. We now have our a and b using a different method. Okay, so now let's leave all this and go back to our question. Okay, let's put this off. Let's go back to our question now, which is this question here. We want to do the integration. So I'm going to clear this side. Let me clear here. Now that we have found our a and our b, it means we have essentially completed the partial fraction. We now have to take this back to our question, which is about integration, and connect the dots. Now I'm going to take you back to the original question that we had. So let us come here. We have the integral of x squared plus x minus 7 over x squared plus x minus 6. This essentially means it is the integral of, this is the integral of 1 x. Remember, we already had a 1 when we converted this to a mixed fraction. So we have integral of 1 dx minus, I'm going to put a bracket here. I'm going to introduce the fractions that we got from our partial fractions, which is, and I'm going to integrate them separately. So it means I'll be integrating here minus 1 over 5 over x plus 3 dx. The minus 1 over 5 is our a, by the way. Then plus the integral of 1 over 5 over x minus 2 dx. Remember that this is our b that we got is 1 over 5. Now let us close the bracket. So this minus sign is working on these two fractions. So let us simplify the fractions further. I'm going to repeat here, integral of 1 dx. There's a minus here and a minus, so it's going to be a plus. So we'll get a positive sign. And then I'm going to take out this 1 over 5, which is the numerator. I'm going to take it out and put it before or behind the integral sign. Integral of 1 over x plus 3 dx plus 1. No, this is not plus, it's now minus because the minus sign outside the bracket is acting here. So we've got minus the integral of, right, let me put 1 over 5 also outside, 1 over 5, the integral of 1 over x minus 2 dx. This is what we have. Now, if you look at these two fractions, both of them, they satisfy this fraction here and this fraction here. Both of them are in the form integral of f prime of x over f of x. In other words, the numerator is the derivative of the denominator. And we know from our formula sheet that if we have something like this, the answer is the natural logarithm of f of x plus a c, which means we are essentially taking the natural logarithm of the denominator and then we add the general constant c. That's what we have to do to integrate that. And there is no really a problem in integrating 1 dx, because the answer is just an x. That's what we have. All right, so let us complete our question. So we have here x plus the 1 over 5 times the natural logarithm of x plus 3 minus 1 over 5 times the natural logarithm of x minus 2 plus the general constant c. This is our final answer. Thank you for watching the video. If you have any comments, write in the comment section below and I will respond to you. Otherwise, give a thumbs up to the video, subscribe to the channel and share with your friends. Thank you.